Hi, everybody. Hopefully your practice on the last day of identities went very well. And today what we're going to jump into is our Trig Identities 2 day. So the assumption I'm going to make at the beginning of this lesson is we've gotten somewhat comfortable using our quotient and our Pythagorean identities to be able to get left side to look like right side. And that we've spent some time playing around with some of those problems where we're starting to feel like these problems are like puzzles. And can we find our way or sort our way through this puzzle to eventually get to the end goal of left side looking like right side? So, what I'm going to talk about today then are some specific strategies you can use to be able to work your way through. Now, in the ideal situation, what I would have liked would have been to be able to put up an identity like you see on the screen and then give everybody a few minutes to play around with it. And then we can talk about the strategies we see. I would be talking to you about the amount of struggle you need to experience. That we often learn an awful lot more through that struggle than what we do through our success. That I'm going to argue, when you pause the video today, pause it for a while. Really struggle your way through. Don't just be satisfied with left side looking like right side, although you should be very happy when that can happen. But also then focus in on, when you see a solution to any of these identities, am I taking an efficient route through that process? Do you see something that you never thought to try? All these things we want to do to get to the point where we can feel comfortable stumbling our way through an identity, but having so much experience with it that we can recognize certain patterns that we can follow that can help us out. So, let's jump in for today. I'd like everybody to pause the video and try to go through and prove 1A. Okay, we're back. So, if I was to play around with this example, I think what I would be doing would be playing with the left side. The reason why I would manipulate the left side is because I can see an operation right off the bat that I know that I can follow. I can square that binomial. So if I were to expand those brackets, then I can square the first, multiply those two together and double it, and square the last. If I happen to see that, I'm having a focus over on the right side. What I really like is my right side has a term 2 sine x cos x, and I have a term 2 sine x cos x from the left side. So I like the fact that those are both there. Now I take a look at what's remaining, and hopefully that is jumping out at you. That what you have is a sine squared plus cos squared, and we know our Pythagorean identity says that that is equal to 1. I used my Pythagorean identity. I'm going to quote it. And there we go. Now, I would have had some other people that may have gone the other direction. And what I want to do is want to show you an alternate way to be able to work through that problem. Perhaps we started with the right side. I'll be honest with you, I don't know why we would, because there's such little there, but we still could. And maybe we see the 1 on the right side, and we know that we can replace sine squared plus cos squared for our 1. Now, instinct-wise, I have to be honest with you, that action that we just took on the right side, if I was to go through and try to prove 20 identities, I might do that once. Me replacing 1 with sine squared plus cos squared is a limited action for me. Unlike in the blue solution, me replacing sine x plus cos x, sine squared plus cos squared with 1, I do all the time. Now, if we were to look at that purple line, we might be stumped as to where to go in this instance. And I just want to show you that I think this action could pop into our heads. And the reason I say that is because we quite often get used to seeing polynomials that would take the form of a squared, and then you have a middle term of like 2ab, and then you have a last term of b squared. something squared, and a combination term in the middle. Maybe we can then see that what we could do is we could take that purple solution and we could factor it. I would be looking for two numbers that multiply to give 1 and add to give 2. That would be 1 and 1. I know that we wouldn't factor it into sine x plus cos x and sine x plus cos x, because bad form would say if you have two of those same factors, then write it as a perfect square. So, two ways to be able to work your way through problem 1a. Okay, what we're going to do is we're going to start to pick up the pace as we go through these identities, and we're not going to provide multiple solutions. It's up to you to try to see the efficiency factor of different routes through. So you'll see the identity that we have to prove in B, and right now I'd like everybody to pause the video and jump in and give it a go. Okay, we are back. So in this instance, I would be working my way through and manipulating the left side. The reason for it, my left side has so much more stuff in there. So the first thing I think I would do is, since I recognize that I have sine squared over cos squared, I can actually use my identity in that form. It's really important for us, if I make a note off to the side, that sine over cos, if I were to square that whole fraction, then that means that I would square the top and I would square the bottom. So sine over cos all squared is equal to sine squared over cos squared. Notice that sine over cos is my tan. That is my quotient identity. Don't feel like you would have to go backwards in this case then and rewrite sine squared over cos squared in this form to be able to use your quotient identity. You are completely fine then to use a manipulated form of your quotient identity. That being, sine squared over cos squared is equal to tan squared. Now the rest of that line is 1 over tan x. And if I were to go through then and multiply those two together, that's going to get me tan x, because when I cross reduce, those tan x's will divide out. Now I've got my left side looking like my right side. I have proven my identity. There is another way through this one, and I would like to show you very quickly that we could have manipulated the left side a little differently. That I think I would have had a number of people say, I know that tan x is sine x over cos x. And therefore they would have subbed in and used their quotient identity there. I also left out my quote up above. When they get to this instance, they have now subbed in, and my action is to always simplify. And so I see in that second fraction that I have 1 divided by a fraction. So to divide fractions, I am going to flip and multiply by the reciprocal. And now I get to this instance where a cos x will divide out one of those cos x's, and a sine x will divide out one of those sine x's. And this expression then would be the 1 sine x on top and the 1 cos x on the bottom, which I could then go ahead and replace with tan x by using my quotient identity again. So, two different routes through B. Hopefully we got one of those routes. Okay, I'd like you guys to take a look at C. Let's pause the video right now and try to go through and prove C. Okay, we should be back. And so, like the previous, I think I would work on my left side because, again, there's more stuff. I have no idea where to go in terms of where my pathway is going to lead me. However, I do see a tan x on that left side, and I know at the very least I can always replace my tan x's with sine over cos. Notice I'm being very clear about what is my dominant fraction line. I just went through and used my quotient identity. I'm going to quote it. Well, now that I've subbed in, my next decision is made for me, and that is I simplify. What I want you to do is focus in right now on the top of that big fraction. That for me to simplify, that means I'm going to have to get a common denominator. And so one of the very common approaches that we deal with is getting a common denominator when we add or subtract two fractions together. My common denominator is going to be cos x. The first term will then become sine x cos x when I get its common denominator. And my last one didn't need changing because its denominator was already cos x. Notice I may need to extend some of my fraction lines to make sure I can clearly see my dominant fraction line. Okay, I got to that point. I haven't fully simplified yet. So I now have a fraction divided by cos x plus 1. That would be the same thing as this line. Sine x cos x plus sine x all over cos x times 1 over cos x plus 1. We know to divide means we flip and multiply. You never have to show that green line. We would be totally fine with you coming in on this line. I then have my top. Now what I need to do is take that bottom of cos x, just to be clear, and now multiply it by my cos x plus 1. And so you can come right in on this blue line. My only suggestion to you would be, let's not expand this in and fully simplify yet, because we might have to take an action where we then have to backtrack. I like that last blue line that I put down, and maybe you can see where we would go next. I somehow have to get this to equal tan x, my right side. Which means I really got to clean up a lot of stuff. Well, perhaps we notice that I can't really simplify with the exception of expanding in the cos x on the bottom. But that's not really going to get me anywhere. So if I can't simplify, then what I can do is unsimplify, and one of those actions I can do would be to factor. If I factor my numerator, then I get sine x times cos x plus 1. I have a common factor of sine x. My denominator is still that. And maybe you can see why I didn't want to follow that red and expand in on the bottom. Because now I can divide out my common factor of cos x plus 1, and that leaves me with sine x on top and cos x on the bottom. And I love that because that's equal to tan x because of our quotient identity. So, couple actions that I want us to be conscious of in this proof. The first one, common denominators. It's going to be a really common approach for us. An action that we're going to do over and over again. The next thing would be common factoring, especially when it can lead to dividing out of common factors. So there's two actions that we want to make sure that we know that we have in our back pocket. Let's try another. Okay, I've thrown a big, ugly one at you now. So for us to be able to work our way through on this one, I don't know which side we manipulate. We have so much stuff on both sides that we could work our way through either side to try to make it look like the other. I might be tempted to play with the left side, and the reason that I would want to play with the left side is just because I have more terms. Yes, it is one fraction on both sides, but I have three terms on the top and the bottom. So if we're going to start manipulating the left side, then we should be pausing our proof, our video, and giving this one a shot on our own. Okay, we're back. One of the other strategies that you might want to use as you work your way through is the idea of having the same trig ratio as much as possible. If things are the same ratios, then perhaps you can divide out common factors, you can collect like terms. As things are different ratios, it might limit the actions you can take. So notice that on the top of my fraction line, I have sine squareds and cosexes. Same on the bottom. Because I have sine squareds and cosexes, I can't collect them. So one of the actions I might want to take would be to replace my sine squared with 1 minus cos squared. That would be me using my Pythagorean identity on top. Well, I can do that exact same thing on the bottom. And what I get out of that action is I get everything in terms of cosexes. And if everything is the same ratio, then I have some options. So I just made a substitution. Next thing I look to do is to simplify. And so I can at least cancel out my 1's on top. 1 subtract 1 will cancel out. And I can clean up a little bit on the bottom because I have a constant of my 1 minus 3, negative 2. Okay. The first thing we're going to not do is to try to divide out the cos squareds because we see we have multiple terms on top and bottom. It's not a common factor. We can't divide out. Okay, we get to that point and we cannot simplify any further. So we may try to unsimplify, which means factor. Now, for a lot of us, if we take a look on the top, we can now deal with the fact that we have this negative cos squared and a positive 2x. I have two terms. They both have a cosx in it. Then what I can do is I can factor that out, and perhaps I factor out like a negative cosx. That would leave me with a cosx from the first term and a negative 2 from the second term. Now in the denominator, I have three terms. And I'm hoping that when we take a look at that denominator, we might actually have something jump out at us. I'm going to jump up to the top right of the screen just to draw to your attention that what you might have if I allowed cosx to equal a is I could replace all of my cosx's with an a, and you may see that this denominator is really just a trinomial, and specifically a simple trinomial. So we should be good to factor that expression. However, maybe we don't like having that leading term be negative. So if I was to factor out that negative from all the terms on the denominator, then maybe we would find it easier to factor that remaining trinomial. Well, at the very least, I could divide out the negatives now. And so my top becomes cosx times cosx minus 2. And my bottom is now me trying to factor that trinomial. So if we struggle to see that on the denominator, then maybe we can look back up to the top right corner and say, well, if I factored out that positive, I would now be looking for two numbers that multiply to give 2 and add to give negative 3. So back with my red solution, I could factor that into a cos x minus 2 and a cos x minus 1. If you re-expand the denominator, we'll notice we would get back to the original expression. I love the fact that it factors that way because now I can divide out my cos x minus 2's, and that would then leave me with a single cos x on top and a cos x minus 1 on the bottom. Okay, where do we go from here? Well, we have a number of options. And so what we might attempt to do in this situation is we say, I've hit a snag. I got to a point where I can't simplify. And so instead then, I jump over to the right side. And what I'm going to do is now I'm going to try to manipulate the right side to make it match up with my manipulation of the left side. So as I take that right side, one of the first things I may notice. So now my eyes are coming all the way back up to the original right side. On top, I have a common factor of cos x. So I can factor out that cos x from the top. On the denominator, I have a negative sine squared. Well, I know that I can always replace every sine squared with 1 minus cos squared. Okay, I can leave my top factored. And now I can simplify the denominator, so I can go ahead and expand in that and just write it in proper form. So I'll put the cos squared first and the minus 1. Okay, I've hit a snag again. But maybe through our experience the first time, we may see where we need to go. Now I'm just going to shrink this down a little bit to make a little more room to work with. But maybe I can look at the bottom and notice, like previously, this denominator can factor. What I have is a difference of squares. And so when I factor that denominator, it will factor into conjugates. Cos x plus 1 times cos x minus 1. My numerator remains unchanged, but I love the way that factored in the denominator, because now my cos x plus 1s will divide out. And I'm able to simplify that down to cos x over cos x minus 1, and I am done. Nice. My left side looks exactly as my right side, and I have proven my identity. I would throw that one into the doozy category for us. That one's going to probably challenge us significantly. Let's keep them going. So now we take a look at E, and you may notice something that jumps out at you a little bit. I want you to look closely at E. As we look at E, you'll notice on the right side, we have a symbol there that we haven't seen in a while. And so I just want to draw back to your attention a little review from a ways back. You happen to see cosecant x. And we maybe remember that that's one of our reciprocal ratios. We just maybe don't remember which one it is. However, if we do notice that it starts with a co, that means that its reciprocal can't have a co. Well, of all of our primary ratios, the only one that doesn't have a co would have been my sine x. Now, we don't worry about tan x, because remember, we never mistake our tan. So, what that means then is these two ratios are related. So, as a quick review for us, a couple things that we're going to want to make sure we are comfortable with. Things that we have in our back pocket. Remember that cosecant x is equal to 1 over sine x, that secant x is equal to 1 over cos x, and cotangent x is equal to 1 over tan x, are three reciprocal identities. So now that we have those in our back pocket, we can then jump back in and start playing around with E. So let's pause the video, see if we match up in the end. Okay, we should be back. So I'm hoping everybody jumped in and started playing around with that left side, because again, there was more stuff. You see a tan, and so we can replace it with sine over cos. Because you saw a tan squared, then we know that we can replace that with sine squared over cos squared. There is me using my quotient identity. Well, every time I sub something in, my next action is to simplify. So on the top, I need to add together some fractions, which means I need a common denominator. I can get my common denominator of cos squared, and that is my numerator of my overall fraction. Now, I just want to draw to your attention, in case we had any hiccups there, we can still see the 1 in the cos squared over cos squared, and we can see the sine squared over cos squared in the other. There's our confirmation of our common denominator. Okay, I still haven't fully simplified, because what I have here is a cos squared plus sine squared. And now to divide fractions means I flip and multiply. That perhaps we get to that point. I would hope that we would be okay to jump to this as your next line. 1 over sine squared. However, maybe we can't see it. It might help if I wrote this on the left side. Maybe we can see it now. Take a look. We have cos squared plus sine squared. That is my Pythagorean identity. Also, we have a cos squared that will divide out with that cos squared. So that whole thing shrinks down to 1 over sine squared. But I want to show you an alternate way that you could express it. So we're going to get rid of all of that stuff, because if we're comfortable with this, then maybe we can see that these cos squared x's, they're going to multiply out. Maybe we can also see our Pythagorean identity now, which means we could jump to this as your next line. 1 over sine squared x by quoting Pythagorean. Please feel free to go through and jump to that line if you are comfortable. If not, then you know you can always flip and multiply and divide out common factors. We do get down to that point, and we should be good then. That 1 over sine squared is a version of our cosecant ratio. And so we could then jump straight to, that then is cosecant squared, and my left side equals my right side. I would have a bunch of people that would have began the problem jumping over and writing the right side as 1 over sine squared by using that reciprocal ratio right off the bat. They would not have had to would not have needed to write this last line, and could have then told the reader that left side equals right side there. Okay, you don't have to quote any of your reciprocal ratios. Those ratios are known. Okay, so now we have our reciprocal ratios that we can use as well. So let's jump in and get one more practice problem. Okay, I want you to take a look at the screen, and I would argue that this one is about as ugly as it will come. So I want you to pause the video and start working your way through this one. Know that if you hit a snag, you should. Your job is to kind of breathe and work your way through it and see what your instinct tells you to try. Okay, pause the video now, give it a shot. Okay, we're back. I've shrunk it a little bit to put up in the top because I am anticipating that this one could be pretty ugly. I'm going to talk out what I see in this problem as we work our way along. First off, I take a look at that top left side, and there's a lot of stuff there. The right side has a lot of stuff too. I don't think it matters which one we play with. So I'm going to jump in on the left side first. Now, I look on top, and I have a couple things that I can do. I notice that I have two terms on top. That is, I have a sin x cotangent x and a sin x cos x. And in those two terms, I have a common factor of sin x. And so maybe I work my way through and I factor out my cotangent or my sin x to leave me with the rest. Okay, I get to that point, and now maybe I'm a little stumped. Well, I do notice that I have cotangent in on the inside, and I know that that's a reciprocal ratio. So I can replace my cotangent with 1 over tan. Now, since that's been replaced with tan, then I know that my tangent is my quotient identity, and I can replace my tan with sine x over cos x. And now that I have 1 divided by, that whole thing could be written as... Now, you might notice that I've gotten pretty sloppy as we've progressed. The reason for that is you don't have to show us any of that work. If we know, and we take a look up in the top right corner, that tan x is equal to sine x over cos x with the quotient identity, then its reciprocal ratio has to be the reciprocal of the quotient identity, cos x over sine x. And so rather than going through this whole process, let's get rid of all of that and save all of that work. And instead, let's just use our quotient identity again. What that means is I can replace cotangent with cos x over sine x. And that is me still using quotient identity. Okay, now that I've subbed it in, I simplify. So on the inside of those brackets, I can get a common denominator. That common denominator is going to be sine x. That is all still over that dominant fraction line of cos x. But at least now that I've done that, I notice my sine x's will divide out. And so this side can then become a cos x minus cos x sine x all over cos x. Now, we could unsimplify this and factor the top. However, we might see that on the top of my fraction I have 2 terms, on the bottom of my fraction I have 1 term, but all 3 of those terms contain a cos x. And so I can then divide out a cos x from all of those terms, and I could shrink that side down to a 1 minus sine x. Okay, I got to that point where I can't simplify that thing any further. Okay, it's time to jump over and play around with that right side. So I'm going to play around with the right side and see what I can come up with. Well, on the denominator, I notice kind of the same pattern as what I began. I have 2 terms on the bottom. Both of those terms have a secant in it. So I'm going to factor out my secant from both terms. Well, I know that secant is 1 over cos. So I can replace that with my 1 over cos. Well, I get to this point, and here's where we've got some options. I do have this 1 over cos x that I could expand into my brackets. But I also have that 1 over cos x that is being multiplied by everything on the bottom. And if that's the case, then I could do this division operation with the 1 over cos x. You have 2 options to work your way through. If you are very comfortable with your operations, I would suggest the latter. However, if we're still a little unsure of our operations, then I would go with the former. So let's go ahead and let's just put the blinders on a little bit, and let's go ahead and expand in the 1 over cos x. My dominant fraction line isn't looking very dominant. I'm going to make it a little bigger. Okay, I can continue to keep going with this, so that means I can simplify my denominator into one fraction. Luckily, they already have a common denominator. Well, now that I get to this point, I am now taking my cos x, and since my denominator is one fraction, then to divide by a fraction, I am going to flip and multiply. And that's going to get me to a cos squared x over 1 plus sine x. And now that thing is fully simplified, but it doesn't look like the ending of the blue. I can see where to go, though, and I'm going to be a couple steps away. One of the next strategies that you can look at is look at that left side and notice that the only trig ratio I have in there is a sine. So when I look at my right side right now, I might want all of those to be sines as well. That's going to motivate me to change that cos squared. And I have an identity I can use because I know cos squared is 1 minus sine squared. And there is me using Pythagorean. Now that I have that, this is just like the last one. I notice on top I have two terms. I have a difference of squares. And so I can factor that difference of squares into 1 minus sine x and 1 plus sine x. I'm just going to shrink that down just a little so we can see it a little clearer. And so again, if I factor a difference of squares that I'm going to have conjugates, my 1 minus sine x times my 1 plus sine x. And now that we get to that point, we love seeing that because my 1 plus sine x factors will divide out, and I am left with a 1 minus sine x. And then I can exhale because I finally got down to my left side looking like my right side. Okay, you saw a bunch of strategies today. The idea of if you see a tan, replace it with sine over cos. Fight off on the urge of replacing your ones with sine squared plus cos squared. If you see a sine squared, replace it with 1 minus cos squared. If you see a cos squared, replace it with 1 minus sine squared. And now you have all of your reciprocal trig ratios. Your cosecant, your secant, your cotangent. I think what we need now is to get a ton of practice going through and solving these puzzles. Best of luck to you.